Hello, and welcome to lesson 14 of this introduction to calculus with Wolfram U. The topic for this lesson is related rates. So let's begin with a brief overview of the lesson. So, in most problems, there'll be more than one thing that is changing in relation to something else. So, for example, you might have, of course, time varies, but then two other things vary with time. And as a good instance of that, let's talk about a ladder that's falling along a side of a wall. So that's a ladder, it's falling along the wall, and there are two things that are changing. There's the height of the ladder from the top and the distance from the base of the ladder to the base of the wall. So both these are changing as the ladder falls. And of course, the rate at which the height is dropping and the rate at which the distance is increasing are related. So that's the theme for today's lesson, related rates problems. So let's begin with an example, and that's exactly the one we took early on of the falling ladder, but now you've got numbers in it. So you have a ladder that's 5 feet long, and it's resting initially against a wall, and then it starts to slide down. So let's say it slides down away from the wall at a rate of 0.5 feet per second, and the bottom of the ladder is 4 feet away from the wall at a certain point. The question is, how fast is the ladder sliding down at that time instant? So the first step in this case is to assign variables to whatever is changing in the problem. And there are two things that are changing. There is the height y, let's say, and the distance x. Next, draw a picture of what's happening. So the pictures over here, you have that's the distance for the base, that's the height, and that's the actual ladder over here. Okay, now to find a relationship between x, y, and 5 over here, you recall the Pythagorean theorem from geometry, and that says that x square plus y square is 5 square. So that's the relationship that we require between x and y. Now, because we want to find the rates, we differentiate that relation with respect to t, and what you get back is 2x times x prime plus 2y times y prime equals 0. Now keep in mind that x is 4 at that point, x prime is 0.5, so you get back an equation which is simpler than the earlier one, but you still need to know what y is. But then you recall the Pythagorean theorem, and that lets you find y as being 3. So once you've got y, you can plug that back in over here into the earlier equation, that's this one, and you get back the rate of change of y as being negative 0.666667. So the ladder is sliding down the wall at a rate of 0.67 feet per second approximately. And the question is, why is that sign negative? Well, it's negative because the top of the ladder is actually going down. So having solved that one problem, let's set up a general strategy for solving such problems. So first, always try to understand the problem. Make sure you know what you're asked to do. Next, assign symbols to all variables x, y, etc. in the problem. Now, to help yourself understand the problem better, draw a picture. It doesn't have to be a very elegant picture, but it should be just enough for you to understand what you need to do. Next, the creative part. Find an equation that relates all the variables in the problem. And usually, something from geometry is going to help you to do that. Next, differentiate the equation with respect to time using the chain rule. That's the key rule for today's lesson. Now, you may already know a few variables, but you need to find any remaining unknown variables before you can proceed. Once you've done that, then you substitute all the information that you found out and solve for the true unknown quantity in the problem. So that's the general strategy for this lesson, and let's try and apply it to a few more problems. So here you have a spherical balloon that's being filled at a rate of 50 centimeter cube per second. And the question is, find the rate at which the radius is increasing when the diameter is 25 seconds. Now, in this case, the volume and the radius are both functions of time. So here's the picture. You have the radius and the volume as being the variables for a problem. Next, you know from geometry that the volume of a sphere is 4 over 3 pi r cube. So that's a relation. Next, you differentiate that relation and you get back an equation relating v prime, r, and r prime. But of course, you need to first find what r is at that time t, but you know the diameter is twice the radius, and the diameter is 25, so radius at that time is 12.5. So you plug back all the information that's known to you, and you find that the radius is increasing roughly at 0.025 centimeters per second. The third problem, let's talk about a watchdog. So there is a cat that's walking down a street at 3 feet per second. Now, a dog is sitting and sees this cat and stays focused on it, doesn't actually move. But then the dog is known to be 6 feet from the street and the cat is 8 feet from that point. And the question is, how fast is the dog's head turning? So there are two things that are changing. The dog's head is turning and the cat is moving away. So the question is, what do you do over here? Well, you first draw a picture. That's the angle of turning for the dog's head. That's the distance traveled by the cat down the street. And this distance over here is given to us to be 6 feet. Now, in this case, you have a right angled triangle, so you can use the tangent of theta as x of t over 6. Once you have a relation over here, then you can differentiate it, and you find that you have another relation for theta prime now, but now you need to know what the secant of theta is. Well, the point is that you have the Pythagoras theorem, so you use that to work out the hypotenuse of the triangle at that time. It turns out to be 10. Use that to find the secant, like I've done over here. Once you've done that, you can plug in all the values and work out the rate at which the dog's head is turning. So the dog's head is rotating at 9 over 50 radians per second, or about 10.313 degrees per second. Okay, on to the final problem for the lesson. So oil is being poured into an inverted cone at a rate of 3 meter cube per second. That's the rate of change of the volume. You're given that the cone's height is 10 meters, radius is 5 meters, and the question is, find the rate at which the oil level is rising when the oil is 5 meters deep. So you've got two variables over here, the volume and the height. So that's a picture for the problem. Now, you know from geometry that the volume of a cone is given by 1/3 pi r square h. So that's the equation for the problem. But notice that you in fact have V, H, and R. And in fact, you want to work only with V and H. So we need to do a bit more work. So you recall that when you study similar triangles, then you could find a relationship between the radius and the height. So in this case, the radius is going to be half the height in the oil tank, because by similarity, any cone within the tank is has radius equal to half the height because you have the initial ones in the same ratio. So here's the volume equation with that relationship. You differentiate it and you plug in values, and you find that the oil level is rising at 12 over 25 pi meters per second. Okay, so that brings me to the end of the lesson, but our main objective here was to solve problems which involved related rates. So what we did was we set up a general strategy for these problems. Then we solved a few of them, but in each case, what you need to do is to use the given information and then apply some geometry, typically, to get the equations required for the problem. So that's the end of this topic, and in the next lesson, we'll talk about linear approximations. But before we do that, do review this lesson. This was a pretty advanced application of calculus. It's just that we now know calculus so well that we can apply things quite easily. But do review this lesson, look at the exercise, and you should be ready for the next one on linear approximations. So I'll stop over here. Thank you.